Okay, so let's continue. We will discuss this structure file syntax in more detail. And one thing we have used before, but only by using the mouse menu. So when we switch parameters from fixed to refined, it changed the code for us. But I want to explain what actually happens exactly. So on the left, you can see the three parameters EPS1, EPS2, and EPS3 from the control file, the sub file. And as I mentioned, only EPS2 is refined. And on the right-hand side, you can see what the syntax looks like for refined parameters or fixed parameters. So if we just write EPS1 equals 0, that is just a fixed parameter. It will never be changed. It will never be anything other than 0. If we want to refine the parameter, we add the prefix param to it. This means it's now parameterized. It's now released for refinement. And this is a bit of a quirk in BGMN again. In the control file, the sub file, we have to number these refined parameters. So we have to add the index n, which is a continuous number from 1 to n. And in the structure files, we don't need that. For some reason, I don't know, it must be related to how it's read by BGMN. So sometimes you will see that it's numbered, and in the sub file and in the structure file, you will see that it's not numbered. But the important part is the param prefix releases this parameter for refinement. If we remove it, it's fixed. And then we can additionally add limits to restrict the refinement range. And after the initialization value, so in this case 0, we add an underscore and then the lower limit, and then the carré symbol, and then the upper limit. So as it is shown at the bottom of the screen. So this is what Profex does automatically when we use the mouse menu, the context menu, or when we use the F5 and F6 shortcuts to toggle parameters between fixed and refined. One more thing, sometimes it is possible to select from the menu refine anisotropically for parameters that cannot be refined anisotropically. For example, coordinates or the cell parameters. These are not anisotropic parameters. So if you choose anisotropic refinement, Profex just removes the limits, which is kind of an interpretation of refine more or refine without limits, something like that. So it's not ideal. Maybe I will change this and so make sure it's not possible to select anisotropic refinement if the parameter does not support it. But at the moment, it will just remove the limits. So this is the syntax we use in the structure file to distinguish between refined and fixed parameters. Now, in all structure files, you will see a few lines starting with goal. And I want to explain what this is. Goal is another word so in BGMN terminology means results. And there are two different kinds of results, direct goals and indirect goals. And these are distinguished by what follows after the goal keyword. Goal equals is a direct goal, and goal colon is an indirect goal. And it's not very intuitive, but I will try to explain, and then it's documented. And if you will ever need this yourself, you should be able to find it on the slides here. A direct goal means nothing else than write the result to the output file. So when we write goal equals grain size 111, this means grain size is a built-in function in BGMN. It converts the B1 parameter to an actual crystallite size in nanometers. So this is a built-in function that returns some kind of result. And by adding the prefix goal equals, we instruct it to write the result to the list file. That's all. And then the grain size, it accepts HKL parameters, so we can specify in which crystallographic direction we want to get the crystallite size. We could add multiple lines. For example, in an anisotropic, in a needle-shaped crystal, we could ask it to print the results in 001 direction and in 100 direction, if that's what we are interested in. Now, goal column, so the indirect goal, is a bit different. It declares a new global variable. So what we are doing in this line, goal calcite equals Gewicht, we define a new variable called calcite, and we assign it the value Gewicht. And by adding the goal column prefix, we make this value of calcite, so this variable, available globally. And this, I know it gets a bit complicated, but this means we can access it from the refinement control file. Gewicht, every phase has its Gewicht parameter. So when we try to access the different Gewichts from the control file, we don't know which phase, so we cannot access these values because it's present in every phase. But once we export it as a global goal, we can access this value. So if we look at the refinement control file, for both phases, I assigned the value of Gewicht, and with some correction factor, that's the Brindley correction for microabsorption. But basically, I assigned the value of Gewicht to a new variable called calcite that is globally accessible because it's a goal. For appetite, I did the same. I assigned the value of Gewicht to a new variable called hydroxyapatite, globally available or accessible. And in the control file, here I'm reading these two Gewicht variables with their specific new names. I can access them now. And that's how I can determine the sum of all scale factors and normalize them to the phase quantities. Normally, you don't have to use goals. It's by default, it's always a Gewicht goal, and the grain size is always added as a direct goal. Normally, you don't do that. But if you, for some reason, do your own calculations, this is how it works. And I will show you a few examples for potential calculations, what we could do with these statements. Let me just set this back. So, okay. So in the appetite file, as I mentioned before, we are instructing it to write the grain size in two different crystallographic directions to the results file. And in the results file, we will get exactly what we asked for, the crystallite size in direction 001 and 100. In this case, it's a high temperature apatite. So even though it was needle-shaped after the precipitation, we calcined it at 1000 degrees, and then the particles get more or less almost spherical. And you can see that is basically the same crystallite size in all directions. So that is no surprise. If the particle was still needle-shaped, I would expect very different sizes along the z-axis than perpendicular to the fibers. Other examples, I could calculate the volume of the unit cell. This is the equation for a hexagonal cell. And if I only do that in the structure file without making it a goal, it will not write the result to the output file. So I have to add the statement goal equals and then the formula to make sure it shows up in the list file. Or another example, I could calculate the mass absorption coefficient for this phase and write the result to the list file. Indirect goals, that's what I already mentioned. We assign the value of Gewicht to a new variable called hydroxyapatite. The animations are a bit messed up here, so sorry for that. And then we can access this in the control file to calculate the normalized phase quantities. That's what's going on there. Other examples, again, we could declare a new variable called vol appetite and assign it the value of the unit cell volume. And then we could access this and do whatever we want with this variable. Or the mass absorption coefficient for appetite, Mach appetite, and then access it for whatever we want to do on the level of the control file. That's again a summary which variables can be accessed, which kinds of goals, where do they appear, and how can we access them, but I will not spend more time on that. So the next detail about structure files I want to discuss is site occupancy factors and substitutions. In this example of hydroxyapatite, we already see one specific feature. If we focus on the declaration of the scattering factors, the elements we assign to the atomic positions, we can see that most of them are not followed by a number in parentheses, but the last two, the OH group, is followed by 0.5. And the scheme we are using here is we assign a scattering factor, and in parentheses we add the site occupancy. If it's missing, it means it's fully occupied. So calcium, phosphorus, and all the first three oxygens are fully occupied. I could add the 1.0 in parentheses, would be the same. If I add something other than 1, it means it's partially occupied. Of course, I'm not allowed to add a value larger than 1 or a negative value. That's not accepted. So anything between 0 and 1. That's a partially occupied silicon site. The same if I choose to use the ionic scattering factor. The first silicon was the atomic, the neutral scattering factor. I can do the same with ionic ones. And if I want to co-substitute something on this site, so if there is a certain fraction of silicon and then the rest is aluminum, I would wrap the whole part in parentheses, and inside I would add these two positions, partially occupied, split by a comma. So that's how I declare a substitution in the structure file. And now back in the appetite structure file, obviously the OH group is only 50% occupied, but it's a fixed at 50%. This is a hard-coded composition. 1/4 is aluminum, 3/4 silicon. And we can also refine this ratio. And here's how we do that. We, instead of writing a number into the parentheses, we write a parameter, so a variable. And it doesn't matter which way we do it. In this case, silicon is occupied with the fraction p, and aluminum 1 minus p. So the site is fully occupied by the variable ratio of silicon and aluminum. And then right after, on the same line, right after this statement, I refine the parameter p. And in this case, I decided to start with 0.75 because that's what I used on the left side for the hard-coded numbers. And then I allow this parameter to vary between 0 and 1. So I can go from a fully silicon occupied site to a fully aluminum occupied site. This is how I refine the ratio of these two atoms on the same site. So, for example, in the calcite structure, we could assume that there might be some magnesium replacing calcium. And this is what it looks like in real life. I do not forget to wrap this in parentheses, unlike when we just have one element in case of carbon and oxygen. And then we refine the ratio of the two ions. And after the refinement in the list file, down at the atomic positions, we will see the result. So around 5%, a bit more than 5% of the atoms are magnesium on this site. Now let's turn it up another notch and make it even more complicated. I hope you can still follow me, but this is something we will practice afterwards with the first example. We can get some nice results with the mixture of apatite and calcite with this. But sometimes we want to have even more complicated models for substitutions. So in this case, in the apatite phase, I know from a chemical analysis that my sample contains some sodium. So I assumed that sodium would replace calcium. And I implemented just what I have shown before. Here P is actually the amount of sodium. That doesn't really matter. I will just start at 0, assuming that it starts with no sodium, and then let it refine. But the problem is sodium is monovalent and calcium is divalent. So if I replace sodium for calcium, I will introduce a charge imbalance. The structure is no longer neutral, and this is physically impossible. So what I have to find a way to compensate for this. And usually in apatite, if something like this happens, it's the OH group that changes, because this is a negative charge and it's rather variable. It can also be replaced by carbonate or fluor ions, and so it's a rather flexible site. So I could try to establish a model that allows me to replace some calcium by sodium and compensate it by changing the OH site occupancy. And you will probably need some time to understand this, but I will show how I did it. So these are the sections from the unmodified structure file, and I modified it like this. So first of all, I declared the substitution parameters for both calcium sites before the element line, so outside of the element declaration, because only then I can use it for another element as well. As long as it's written in the element line, I can only access this parameter P before for this element. But if I declare it before or outside of the element line, it's a normal parameter I can use anywhere in the structure file. So I declared two parameters, P, Na1 and 2. These are my site occupancies, so the amount of sodium on the calcium 1 and calcium 2 position. And then I calculated how much OH groups can I have in my structure if I introduce some sodium. And I have to take into account that these two calcium sites and also the OH sites have different site multiplicities. By replacing sodium on calcium 1, I'm introducing a different amount of sodium than if I do the same on calcium 2. So it goes deeply into crystallography now with the site multiplicities, but this is something I have to remember. And that is why you see here I have to correct the sodium introduced to calcium 2 with this factor, because calcium 2 is the only one that has a site multiplicity of 6, and all other sites are multiplied by 4. But like this, I can calculate how much OH do I need in my structure to maintain charge balance. And then I just use these parameters in the element declarations for the calcium 1, calcium 2, O, and H positions. So some more statements. Yes, the parameters I used on several atomic sites must be declared before the E lines, so I can use them afterwards in all E lines. Otherwise, it's only known within a specific E line where it's declared. Okay, so this, you will have time this afternoon to implement this in my example number 1. And the result should be very nice, because this is, example 1 is a synthetic mixture of calcite and apatite, and you will see how much I mixed once you see the result. It's quite obvious. but yeah, we can try this. It's basically just an example to show that we can use these calculations in the structure files to do just about anything we want. It's really powerful. We can establish complex models for substitutions by implementing this. And this is the main reason why Profex, even though it's a graphical user interface, still uses text files. Something like this would not be possible if it would be a point-and-click interface that abstracts everything into a nice checkboxes, mouse interface. So I really did not want to sacrifice this powerful feature with the built-in interpreter language of BGMN, because it's just so powerful. It allows to do so much. So instead, with Profex, I chose the approach to try to help the user as much as possible with the mouse menu, with the context help to provide the information, but we still work on the text files, even though it's a bit scary, it's a bit old style, but that's really also one of the strong sides that we can calculate so many custom things in Profex and BGMN. So this afternoon we will continue to work on example 1. We will implement the substitutions and improve the refinement even more and see what we get. Now for the rest of this lesson, I want to make a hard break and change topic drastically and come back to the instrument configurations. In the latest version of Profex, you will find 2 instruments starting with FZ. That's your instruments. I think 2 different ones, both D8 instruments, Brooker, but 2 different setups. So as long as you don't change these, the configuration, you can use these configuration files coming with Profex for your refinements. But if you start changing apertures or anything like that, you will have to modify them. And if you leave this place and go somewhere else and find different instruments, different configurations, you will have to create your own instrument configuration files before you can use Profex. I know this is a big hurdle for new users. They always pick just something from the long list of instruments and they think, this looks like Panalytical. I have Panalytical, so they use the first Panalytical instrument they find. But this is not going to work. So they get very poor fits because it can be a very different configuration. So I want to show you how we set up our own configuration files, where we find the necessary information, because at some point you will probably need it if you continue using Profex in the future. So as I explained yesterday, we will need a file that contains a description of our hardware. And the schematic on the right is what we find on the BGMN website. It looks a bit scary, but it basically shows a standard instrument beam path starting with the tube, which is called focus here, the target size, then the different slits I showed yesterday in my own graphics. And then on the right side, so this is the standard reflective geometry, Bragg-Brentano parafocusing instrument. On the right side, we see again some slits and the detector here, even with a monochromatic crystal. So this is what we have to provide in the form of a text file to BGMN. At the moment, Profex comes with 70 configurations, and these are all very specific instruments. They often start with a symbol that notates the university or the institute they come from. So it's really, it might be the same instrument as yours, but it can still be set up differently. So it's really important that you use a configuration exactly for your setup. And in previous workshops, some years ago, I had to explain in great detail how to create this text file. But meanwhile, I implemented a graphical instrument editor in Profex, and you can access it if you go to Instrument, Edit Current FPA Configuration. It will open the configuration we use in example 1 in this editor, and you can browse it and click through it and see how I described the RMS D8 instrument. You can still toggle between this graphical representation and the original text file using these buttons above. And also here, it is possible to implement custom calculations, and these cannot be displayed in the graphical editor. So if you do anything fancy, you will still have to work on the text file. But as long as you don't do anything fancy and just implement it using the graphical editor, you can stay in the graphical display and just work there. It's much more intuitive. So what I recommend is you just go through your beam path. You start at the goniometer, so at the very top of the list on the left, and you just check what options you have to configure and make sure that every box contains the correct value. So first of all, check which optical elements you have installed, and then go through them systematically from the tube to the sample to the detector, and make sure on the left-hand side that you always enter the correct values. I would also like to mention that for each optical element there is a second page with a description, and I spent quite some time to describe and give helpful information on this help text. So it should be enough, ideally, so you can decide what to enter on the left-hand side in the parameters page. So as I said, go from the left to the right and just check every module. Once you're done, you should save the new configuration under a different name. Use the Save button, give it some name, and then you have to start the calculation of the profile. That's the button on the bottom left, number 4. So after saving it, press this button, and it will take a while. It can be very slow. It can take minutes sometimes to calculate the profile from this description. But just follow the status bar at the bottom. You will see the progress, and anything between 20 seconds and a few minutes is possible. And then once you're done, the new instrument configuration is available. So you can set it, you can use it in your refinement project by changing the value of the Verzehr variable to your new instrument file. So here it still points to the RMS instrument. You would just change this entry to the new instrument name you selected when you saved the configuration, and then repeat the refinement with the new configuration. So this is hopefully not too complex. The problem is, where do we find all this information about the instrument? And there are different possibilities. It's usually the hardest part to gather all the information we need. But I suggest if you have access to the instrument and to the control PC used to operate the instrument, you should be able to find the information there. The problem arises, or is even worse, if you don't have physical access to the instrument. Then you may have to guess, or maybe you just don't have this information. So the first, my first attempt to find the hardware information is always the instrument control software. I think for Panalytical it was called the data collector back in the days when I used Panalytical. Bruker, it's called Diffrag Measurement Center, and Rigaku I don't remember, I've never used it myself. So there you should be able, I can show at the example of the Bruker software, Diffrag Measurement Center, there's this page, the Da Vinci page it's called. It actually shows my current configuration in a similar approach. So on the left it starts with the tube mount, the radius at the top, and then the different slit mounts, the sample, and then it continues to the right with different slit mounts and ends with the lynx eye detector. So this is basically what I need, or most of what I need, to transfer to the Profex instrument editor. Another option, if we go back here, if you don't have, so that was the control PC, the one connected to the instrument. A lot of this information is also stored in the scan file, especially with modern file formats. They contain hardware information, and we can still access it if we have the original data processing software. So for Panalytical, that would be HighScore. For Bruker, it would be EFA. Again, Rigaku, I don't know. So in this case, you can open the scan file and you can still access this information, as I'm showing with the example of Bruker EFA. It shows me the detector and the opening of the detector and which solid slits are used and the divergence slit. So this is all the information I need for Profex, for the instrument editor. That works with modern file formats, because in the old days they did not save that much information in the files, but nowadays they do. The third option was to hack the raw scan file. So many instrument manufacturers nowadays used XML-based file formats. And XML files, maybe you are familiar with HTML files from websites. It's the same syntax, basically. And we can read them. It's usually a lot of garbage information we don't need, but we may also find the information we need. For example, Panalytical uses the format XRD-ML. And if we open this in a text editor, here in Notepad++, it's kind of human readable. And if we scan through this file, we will find information we need. For example, the goniometer radius is highlighted, or the solid slits, it's a 0.04 radians solid slit, or the beam mask was set to 11.6 millimeters. So this is quite easy to retrieve information about the hardware. Also, the programmable divergence slit at the bottom was set to 10 millimeters irradiated length. This is something we can directly use for the Profex editor. Some other file formats are also XML, but they are compressed. They are actually zip archives with a different extension. For example, the two examples is BRML from Bruker and RASX from Panalytical. We can extract them here in this example, I'm using 7-zip, and it recognizes that it's a zip file. So I can directly extract these files. Or you can just change the extension from BRML to zip and then use Windows Explorer or whatever you use to extract it. And then you will obtain a set of XML files that can also be read as the XRD-ML file I've shown before. If we open this, we find similar information about the radius, this is now a Bruker example. Before we saw a Panalytical example. And somewhere in the huge pile of information, we will find what we need. So, and here's an example from the Rigaku RASX file format. Again, the radius and the solid slit information. So this is the third approach. If we don't have access to the computer or to the original software, we may still find it in the file and hack it and extract it from there. And if this doesn't work, because, for example, you only get a text file with the scan and no hardware information whatsoever, the last option is, of course, we need physical access to the instrument again. The last option is to take a ruler and go measure these distances and openings, and still better than nothing. Sometimes even on my instrument, the position, the distance between the aperture and the sample is not always accessible from the software. So even on my fairly modern instrument, I had to measure certain distances. So that's how we gather the information for our instrument configuration. And then after we started the calculation of the profile, which takes a few minutes, I think it's always very important to verify it by running a refinement of a reference sample. And I recommend the lanthanum hexaboride, the NIST SRM660 sample, because it's a very ideal sample to verify the peak shape. And you should get a chi-square parameter of close to 1 and a very nice description of the peak shape. And if that's what you get, your instrument configuration is very good and can be used. So to summarize all this, first, when we talked about the structure files, I explained how these different goals work. And I also showed an example how we can use the BGMN expression interpreter to establish, for example, substitution models, to couple the substitution on different sites, so to maintain charge balance. And then when we talked about the device files, it's important that it accurately represents your true instrument configuration. You cannot use anything that looks similar. It has to be the same, what you actually use to measure your data set. And you have to try to get this information from different sources, like the measurement software, the data processing software, hack the XML files, or take measurements. And don't forget to verify your new configuration with a reference measurement. After the lunch break, I have prepared 2 examples. Example number 1 will be continuing with the refinement of example 1, the calcite and apatite mixture. We want to implement these 2 substitutions, magnesium for calcium in calcite and sodium for calcium in apatite. You can try with the complex substitution model that compensates OH as well, or you can just try just to ignore the charge imbalance and just replace sodium for calcium to see if it makes a difference. And the second example will be an instrument configuration. I provided 2 files, 2 LAB6 scans, one on my RMS instrument with the standard configuration and one with a modification. And we can try to create this a second configuration for the modified setup. And then that will be the first lesson after the lunch break. And the second lesson, we will discuss some specific refinement challenges. I prepared a sample with a strong texture. I will show you how we can refine this. Another sample contains anisotropic crystallites, so it's a precipitated apatite with needle-shaped crystals, nanocrystalline, and I will show you how to refine this. It takes some special measures to fit it well. And the third example will be a structure refinement with electron density maps, where we can visualize the crystal structure and especially visualize misfits, where they originate from. So that's the plan for the afternoon. Are there any questions now?